Hello. So, what we have done so far is that in our efforts to find out the bands in a solid, in a with a we have worked out the proof of Bloch's theorem. We encountered Bloch's theorem, which is a very powerful theorem, which tells us that the translation of a wave function is just adding a phase to the wave function, which is e to the power I k dot r for a periodic potential, and a periodic potential is what we are studying, because in a real solid the potential is periodic and the period is the same as the real solid the Bravais lattice of the real solid. So, if R is the Bravais lattice, then if R belongs to Bravais lattice, then the period of the potential is also R. So, once that is true, then H of R is of course H of R plus R. So, the Hamiltonian is also periodic with the same period as the lattice, and lattice being defined by the Bravais lattice vectors. Okay. So, now we go back to what we did for 2 atom cases. This 2 atom solid is as I said, is a caricature of the n atom solid. So, now let us graduate towards a large number of solids. So, let me just stick to one dimension for the time being. Life is much simpler in one dimension. We can generalize this to any dimension as we go along. So, this is the periodicity of the lattice, and let me just assume that the atomic distances are a, and let take a equal to 1. Let me take a equal to 1. I can put back that in dimensions and units anytime I want, which I will show you how to do. The distance between 2 lattice points, which is the same as any other lattice point between the nearest neighbor. These are called nearest neighbors. So, this one, for example, has this one has its nearest neighbor, this one and this one. Similarly, the next one, this one has its nearest neighbors, this one and this one. So, that is how nearest neighbors are defined. It is just the nearest neighbor, the English term nearest neighbor, your nearest neighbor. In your house also, at your home, you have nearest neighbors on both sides or on 4 sides. So, these are the same definition works here. Okay. Okay. So, this is the lattice where we will try to first find out the solution of a particle moving in the potential of these atoms, which are located at these points given by cross, with the potential of course is periodic, as I showed in the previous picture, when we did Bloch's theorem. So, remember, the important thing that we have to remember here is that whatever solution we get has to obey Bloch's theorem, and that we can check, or conversely whatever solution we try, we must remember to keep it consistent with Bloch's theorem. Okay. So, that is the reason Bloch theorem is so powerful, because I know what kind of solutions are admissible. Okay. So, remember that example we did for 2 atoms, just for 2 atoms. With an orbital around it, 2 hydrogen atoms for example, we obtained an equation which is H. So, we calculated we took a trial route, right. It is called a variational way to calculate the best possible solution, the lowest energy solution. So, E was psi H psi divided by psi psi, and psi was chosen to be U1 1 plus U2 2. Okay. Now, suppose I have instead of 2 atoms, I add another atom to it, has to be as big. So, let us just draw it as big as the other ones. Okay. So, that is then what do? We just do the same thing. We just extend this by u1 into 1 plus u2 2 plus u3 3. So, that is our scheme of LCAO, linear combination of atomic orbitals. That tells me that a trial wave function of this form is can be tried, and one can look for the variational energy and solve for the optimized problem, minimization of the energy. Okay. So, that is the route we will take again. Let me remind you what we got in the previous case. We got a Hamiltonian which was in matrix form E0 minus T E0. Okay. Remember, T is taken to be real, otherwise I would write minus T star here in the 2 1 element. So, this element, so this is H12, this one is H12, and this one is H21. This is H12 and H21. Okay. Now, if I had one more atom, what would have happened? Well, let us see what could happen. So, now we have the psi has 3 elements. So, remember that psi which appeared in the denominator will now have u1 square plus u2 square plus u3 square, and the numerator will again have similar terms numerator. So, this was then psi h psi will have u1 square plus u2 square plus u3 square into epsilon naught plus the minus twice t times u1 u2 minus 2t times u1 u3. Now, this term I will come back to, plus minus 2t times u2 u3. Okay. Now, if you look at this term, then remember I had a lattice with 1, 2, 3. Now, the term in the red circle, under the red circle, implies that there is a overlap between this and this, right. Now, that overlap of course, in the way I have drawn the lattice is missing, because there is a the factor t is only between nearest neighbors, right. It is the, remember what t was is, just show me, let me show you what t was. Look at what t was. T was 1 V2 2 or 1 V1 2. So, between this matrix element between the orbital at 1 and orbital at 2 of the nuclear interaction of the 2 and of the 1. So, it is the cross term between, by cross I mean it is the matrix element of V1 or V2 between the states 1 and 2. Now, 1 and 2 and nearest neighbor. Suppose I made 1 and 3 on both sides, then 1 and 3 are not nearest neighbors. So, it is a further neighbor, and that cannot be the same as t. That has to, because the wave function falls off. See, the wave functions are they fall off in real space. They are like this, and so, or sometimes they are like this, and so on. So, they always fall off at a distance, and typically that distance is less than even the nearest neighbor. So that the interaction between an orbital at a particular site and its nearest neighbor is much stronger than what it is between this one and its next nearest neighbor. So, 1 and 3 almost barely talk to each other. So, I can basically for the time being I can just throw out this term, right. 2 is 0. So, U1 U1 U2 U2 U3, these terms are there, right. So, so let us just then write the Hamiltonian. I mean, if you now minimize this equation with respect to U1, U2 and U3, you will similarly get exactly the same kind of Hamiltonian. So, you will have a t term between the nearest neighbors and minus t, and the diagonal term will always be epsilon naught, and only 2, the site 2, this one has 2 nearest neighbors, the ones, the site 1 and the atom 1 and atom 3 have no nearest neighbor other than one on the right here for 1 and one on the left here for 3. But if you put a periodic boundary condition, of course, then you make it into a triangle, and every one is a nearest neighbor of the other one. So, that is the case we will not discuss right at this moment, we will come back to it later. In a large lattice, for example, this is, suppose you want to put a periodic boundary condition in a one dimensional solid, then the equivalent description is similar. Here are 6 points, for example. So, what I will do is that I will put them in a circle. One, 2, 3, 4, 5, 6. So, this is the way the periodic boundary condition means that you actually close the loop, and that means this one now 1 has a nearest neighbor which is 6, which is 1 and 6. So, we are not discussing that now right at the moment. Let me just write down the matrix elements, that the matrix of the Hamiltonian that I will get for 3 sites, and where the periodic boundary condition is not used. Again, it will be in the basis of U1, U2, U3 equal to E times U1, U2, U3. So, epsilon naught minus t 0, then epsilon naught here, minus t here, minus t here. Remember, site number 2 has both the neighbors, both nearest neighbors available, whereas site number 1 and 3 has only one nearest neighbor. So, that will be the matrix then. This is the column, this one is the column for site number 2, this is the row for the site number 2, and it has both the on both sides it will get minus t, except for the other ones will not have that. Okay. So, let me just consider the equation for the second row. Okay. So, so this is minus t u1 plus epsilon naught u2 minus t u3 equal to E u2. So, that means E minus epsilon naught into u2 equal plus t into u1 plus u3 equal to 0. Okay. Now, I divide both sides throughout by t, then this is the equation I get. Remember, t is positive, so sign of t has already been accounted for as before, plus u1 plus u3 equal to 0. Now, let me call this quantity as x, let me define it as x equal to E minus E naught by t. Then my equation is x u2 plus u1 plus x u2 plus u3 equal to 0. This is the equation I have to solve. So, this is the equation corresponding to the second row. Okay. So, first let me just stop here and then recap again what we have done. We have just extended the number of protons, number of hydrogen atoms for example, by one more, and that means I have 3 atoms now. 3 atoms puts in an interesting feature in the sense that the number 2 atom now has nearest neighbors on both sides. And in the sense, and the number 1 and number 3 they remain the same equation as before. So, the equation for they have only one neighbor in the open boundary condition, and so those rows will be epsilon naught minus t and minus t epsilon naught. So, the only change that will happen is now in the second row, which has 2 neighbors. So, the diagonal element is again epsilon naught, the off diagonal elements on both sides will now become minus t. Now, can we just extend this to a higher number of sides? Yes, we can. I will just come back to it. So, let me first try to find out a solution for this equation. Okay. So, let me choose a solution which is u of m equal to e to the power I m theta times some constant a. Okay. So, then what do I get? X times a e to the power I. Okay, so let me just remember u sub m is e to the power I m theta into a. So, x times a e to the power I 2 theta plus u1 plus t into, sorry, let me go back. See, remember the solution was t u1 plus u2 into x into u2. u2 I have already put in. So, here I will put a e to the power I theta, here I will put this u3 a e to the power I 3 theta. Okay. And so, that is equal to 0. So, this is x. So, a's will all cancel, x e to the power I 2 theta plus t e to the power I theta plus e to the power I 3 theta equal to 0. Okay. Now, I just take just divide both sides by e to the power I 2 theta, then I have x equal to minus t e to the power minus theta plus e to the power I theta. Okay. Which means that this is minus t into 2 cosine of theta. So, that is x if I choose this as a solution. Now, can I choose this as a solution? Of course, I can, because I know that the solution has to satisfy the Bloch's theorem, and you can easily check that this solution e to the power I m theta does obey Bloch's theorem, because if I go one more lattice spacing, which is plus 1, is basically e to the power I m plus 1 into theta equal to e to the power I theta e to the power I m theta. So, this is my psi, for example, psi at site M, and psi and then I went to psi m plus 1. So, that is e to the power I m plus 1 e to the power I theta into a. So, that means psi of m plus 1 is e to the power I theta psi of m, which is exactly what Bloch's theorem tells me, that if I move by one lattice spacing, which is a Bravais lattice vector in one dimension, of course, this is the only one direction, and I moved one unit, I picked up a phase of e to the power I theta. This theta, of course, I will determine and I will show you later on that it is the same that we got earlier, k dot a. So, this is basically consistent with the idea of Bloch, the theorem of Bloch. Now, x equal to minus 2t cosine theta. What was x? Let us go back. E minus epsilon naught by t was my x. So, let us see what I can do. E minus epsilon naught by t. So, E minus epsilon naught, sorry, there was no t here, I already cancelled the t I divided by t. So, there is no t here. So, E minus epsilon naught by, sorry, E minus epsilon naught by t is equal to minus 2 cosine theta. So, that is what my solution for E is. So, E equal to epsilon naught minus twice t cosine theta. So, this gives me the solution for the energy for this 3-side problem. So, now let us try to generalize it to an n-side case. So, in n-side case, what will happen? Remember that matrix. Remember the matrix E minus epsilon naught minus t 0 minus t epsilon naught 0 minus t 0 minus t epsilon naught. So, this matrix had 3 elements in only the second row. Now, suppose I go beyond 3 sides and I go to 4 sides or 5 sides or even more. So, let us just write down the matrix, and then you will realize that what I am writing is absolutely correct. Then there will be all zeros, because the first side has no other neighbor. The second one will always, the diagonal elements will always be epsilon naught. The second row, for example, had minus t here and minus t here, then all are zeros. Now, the third row again have minus t on its 2 sides, but all others higher further ones will all be 0. So, this will be 0. And so on. So, anything which is not the first one, or the any row which is not, does not correspond to the first atom or the last atom, will always have these 3 elements in that row. There will be not more than 3 elements. There will be a diagonal element which is epsilon naught, and on both sides I will get minus t. So, the matrix has a structure which then is very simple. It is epsilon naught along its diagonals and minus t along the off diagonals, just the 2 off diagonals. So, this will be this will be epsilon naught then minus t and so on. So, this kind of a matrix is called, and the last element, the last column, the last row will have epsilon naught at the last and minus t just next to it, all others are 0. Okay. So, these are all zeros, these dots that I am putting in are all zeros, these dashes that I am putting it are all zeros. So, this is the matrix times u1, u2, u3 dot 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 u sub n for n sides, and this will be equal to e times again u1, u2, u3 dot 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 un. So, that is the structure of this matrix equation, and this is the Hamiltonian matrix that I need to diagonalize. So, again take any element, any row, for example this row, for example if you take this row, this is the third row now, or take the fourth row, it is identical equation to the one that I have just solved in the previous one. There is an epsilon naught minus E which comes from the right hand side, and there is minus t on the left and the plus t on the right. So, the solution that I got for 3 sides is a generic solution. That solution will work for n number of sides. So, that is the beauty of this whole treatment, that all I have done is this in the nearest neighbor hopping approximation, which is the LCO, and using LCO my calculation just reduced to diagonalizing a tridiagonal matrix. This is called a tridiagonal matrix because it has this diagonal element, and on both sides it has a element, it has one off diagonal element on either side of the diagonal. So, that kind of a matrix is I mean this is basically reflecting the periodicity of the problem and the Hamiltonian, and the solution to that, as I said, is consistent with, I chose a solution which is consistent with Bloch's theorem, and that solution gave me an eigen value which is E equal to epsilon naught minus twice t cosine of theta. What that theta is we will calculate, and the beauty of this is that the solution is u m is a e to the power I m theta. So, these are the simple solutions to this problem, and they obey Bloch's theorem, and they give me a variational energy which is what I have just written down. This is my variational energy. So, look at how it is spread out. So, depending on the values of theta, it will be spread. Suppose theta goes from minus pi to plus pi, then in discrete values, which is what, as I am anticipating that I will show you that it is just again k basically k times k dot r. K r here is just one dimensional, so r is equal to a. So, it is just k a and in that case the solution is simply from epsilon naught. Suppose I said epsilon naught equal to 0, that is my 0 of energy, then the solution goes from plus 2t to minus 2t, and there are as many orbitals I started with as there will be solutions, because I can't lose my states, number of states remains the same. So, I have this n number of states starting from plus 2t to minus 2t. So, these are not equispaced, but these are very closely packed. As n becomes very large, and this is a finite width, minus 2t to plus t plus 2t, there you have to pack n states in that, and so these basically form the bands. and these are almost semi-continuous states, because the distance between states, energy difference between states is exceedingly small if n goes to a very large number. So that is the story of band formation. In this approximation, the life becomes very simple, and this is called, this in condensed matter we call this tight binding approximation. Why tight binding? Because it assumes that the electrons are more or less tightly assigned to their bound to their nuclei, but they can talk to the next nearest, just the next nearest neighbor. This is the next nearest neighbor tight binding approximation. You can actually choose higher neighbor interactions also that exist. Depending on the lattice, you may have to choose that as well, but in this primitive form of this calculation, we basically took this LCAO approach and extended to n atoms, and that is called a tight binding approximation, because tight binding simply means that the electron is still considered bound to its nucleus, but not entirely. It is tightly bound, but once it starts interacting with its nearest neighbors, once it starts talking to its neighbors, it becomes delocalized and a band forms. And suppose you have n number of each of these has had only one electron, then of course you know that you have to fill up the lowest n by 2 states, because each state will take 2 electrons. So out of all these n states, you will only fill up n by 2, only up to half of this, and that means you are in a metallic cell. So this part, the part below it, this part is filled up and the rest is unfilled, and this is your Fermi, this will become your Fermi energy, and right above Fermi energy, almost at infinitesimal distance away in terms of energy, there is another state available. So that means there are almost zero energy excitations available, which is the characteristics of a metal. There is no gap for the excitations. So this is what this will in this case, for example, if you have less than twice n number of electrons in this picture, you will get a metallic state. You just keep on filling the number of states. You can put 2n number of electrons if there are n sites, and anything less than 2n will give you a metallic state. So that is the picture of so called tight binding model, and this is a very powerful model. One uses it all the way, even in research people actually use it as a first approximation. When other effects become important, then one starts from a tight binding model and starts to put in the other effects. Of course, there are situations where tight binding will not work. You have to consider higher neighbors, or you may have to completely abandon the band picture, but those are details that are beyond the scope of this. But remember that this is a very, very powerful and nice approximation that one can do, and it just reduces the problem to single particle problems of formation of bands.